Right, now part 3, applications. A short survey, we will skip most of it, but first there are applications in game theory, chapter 8, and a few things will be done. We will not read it all right now. We'll see when we come there. Chapter 9 will have all kind of application for risky theories, and here are what we will do, but we'll see it. Chapter 10 for intertemporal choice, where it's much related with problems of self-control. So that's interesting. Come then. Finally, chapter 11 will be those more fundamental breakaways, how behavioral theories about those gave useful applications. We will see that later. But now we go to chapter 8, application of behavioral insights into game theory, how we get better analysis of it. And I'm gonna do analysis now. You're assuming neo-additive players. Maybe you remember the neo-additive model. It was assuming just like expected utility, but only the best and the worst outcome receive extra weight. It's quite easy tractable model, so you will not mind that we're going to use that. But still, it captures the major behavioral phenomena. So it's a popular model, and we're going to use it also. Consider a game. First, we do a hypothetical game to know how it works, and then we do a real experimental game. In the first game, we assume that 2 strategies for a row player and 2 for a column player. And here are the payoffs. Well, you will have soon a chance to inspect them carefully and what is happening. But first, in all of what I will discuss, we will only look at pure equilibria. Never randomized equilibria will play a role, so you need not look at them. With that understood, my first question to you is, what do you think classical game theory and classical will predict what will be the Nash equilibrium in this game? And you can think about it, and then we will discuss it. And then if you want to think, you can stop the video now. Okay, I'm going to continue. I will tell you what classical game theory, how it is analyzed. First of all, it's quite easy to see that L dominates R. It always gives 1 cent more. So L is played with probability 1. Well, knowing that the row player knows that T is better than B, so he goes for T. And T, L will be the Nash equilibrium, the unique Nash equilibrium according to classical theories. So that's, now I'm going to tell you, we're going to look a bit more at the game, and then we're going to discuss it more. First, note, if you are the column player, you are really hoping and praying that the row player will choose B. That always gives you 5 more than T. So the row player can really help you, but your problem as a column player, you can't do anything about it. But that's a consideration good to know about. With that in mind, I ask you, imagine you are the row player, what would you do? I'm not asking you what theory says, I'm asking what would you do? And I even want to say, what would a wise person do? That may be different than what theory says. What do you think if a wise person has to be the row player, what will that person do? You can think about it, and you can do that stopping the video now. All right, then I continue. I tell you, well, I don't know if I can play the role of the wise player, but I can tell you what I would do if I were the row player in this game. And I would think a column player, maybe, well, here's a figure, maybe a revengeful person. Imagine there's a plausible way of reasoning for the column player to end up with R. It goes as follows. The column player says, the row player can really help me a lot. If he goes with T, he gets only 1 more than B, and he's screwing me by 5. That's really, I don't like it. And then suddenly the the column player thinks, now wait a moment, I can do something nice, I can choose R. I lose only 1 cent for it, which I don't mind much, but it has a very nice property, because if that row player is that selfish, awful person to choose T, I'm really screwing him. I'm serving him well. He gets -9. If he is the nice, altruistic bottom player, he's rewarded by 9. I like that a lot. So I like strategy R is really giving the row player what he deserves. I'm willing to pay 1 cent for it. I'm going to play R. In many situations, many human beings or whatever will reason that way. Therefore, if I am a row player, I reckon with that. I think there is a chance that R comes. Then I get that minus, I'm hit by that -9. I really don't want it. And that's why I go for B and not for T. So if I were the row player in this game, I would go for T. Sorry, B. Now we're going to see what would the neo-additive players do. We're going to analyze the game a bit more, but now we're going to assume not the classical theory, but neo-additive. What happens then? Comes in this slide. First of all, also for neo-additive, the column player L is dominating R. So also on the neo-additive, L has higher value than R. So in that sense, L is chosen with probability 1. That can still be the case. But well, we're going to do the neo-additive utility with the user parameters. You know them, you've seen them before. So I already said the column player will choose L with probability 1. So that's quite simple. But now the row player, more to discuss, more interesting. What will the row player do? Before getting into it, one thing I have to explain to you still. That's the word possible. I told you when I explained neo-additive utility that you always have to think what the word possible means. Here in game theory, we're going to assume possible means that every strategy that is available is possible to be chosen. So even if some theory says that L has probability 1, the row player still considers R to be possible. And I think empirically speaking, that is realistic. So therefore, R is given the status of possible, and it means that it is incorporated in the neo-additive considerations. And then I leave it to you to think about what happens. So you can calculate yourself, and stop the video now. And I'm going to continue now to tell you what comes out. And in fact, you don't really need calculations to see what the row player does. Because you know, if R is possible, then for top, if this -9 outcome gets a weight of 0.2, that's enough to kill it. It's obvious without calculation that in neo-additive, top will be worse than bottom, and bottom will be chosen. Well, here are the calculations. Well, let's first look at top. And you see the 0.2 times -9 is really very bad. It ends up with only 3. Bottom ends up with 5.4, so it's clearly better. So indeed, the neo-additive approach says player 1 will choose B, and the equilibrium will be B, L. Each is the best reply to the others if you do neo-additive evaluation. So therefore, and I think it's empirically plausible. This is, if you want to know what's happening, this is a good prediction, good analysis. Well, there's a saying, and this game illustrates it. Sometimes they say, if you are classical game theories, you only look one side when crossing the street. If you are behavioral game theories, you always look both sides. There are always weird people, the Homer Simpson, you can reckon with all the possibilities. It's empirically realistic to do so. Now let's go to an experimental real data, a game that was really done. You've seen this before with the choice percentages and the references here. And maybe you remember that the equilibria, you could pause the video to inspect the payoffs if you want. But anyway, the equilibria in this game, you will remember they were the corner solutions. They were top L, so let me write it, pure equilibria. Again, we need not consider randomization, only pure. So one pure equilibrium comes here, TL, the other comes here, the outcome is here, BR, the two corners. They are the only two pure Nash equilibria. Both of them assign probability 0 to the NN column, but then classical theory says that one of those will happen. But you see the choice percent in the experiment find very different things. They don't find much of that equilibrium. They find NN, supposedly never played, is by far the most played column strategy. And I think it makes sense. Let us use neo-additive to analyze. And again, it is good if you try to do the calculation yourself with neo-additive. So you stop the video now. And I'm continuing now to tell you what the calculations say. First of all, it's quite easy to see even without calculation that NN is a better column than the others, because NN just gives you 30. And quite you see once, if B is possible, then L is horrible. 0.2 weight for this is completely killing L. Same happens here with R. T is possible, then the 0.2 weight for this -250 completely kills R. Maybe with C, you may want to think a bit more. Is C inferior to NN? Well, it is not so difficult to see. Because even if we take the most favorable probability for C, and that happens when T has probability 1, that is the best for C, then still this 0.2 probability of minus 100 is quite killing it relative to the 30 of NN. And calculations show it. Here are the calculation, this 0.2 weight for minus 100 is completely killing it. It's much worse than NN. So it's completely clear in all your, this was C with probability 1 for T is the best alternative for all other alternatives, all other probabilities, only things are worse. So in every respect, and it's just superior to everything else by the neo-additive model. So the neo-additive model says the column player chooses NN with probability 1. Okay, then how about the row player? Now the row player knows NN is chosen with probability 1, still considers the others to be possible. And the calculations are a close call. I just give them here. The T has the value 27, B has the value 26. That's what comes out of it. So it turns out that T is better according to the neo-additive model than B. So the neo-additive model says the equilibrium will be T and NN. And you see that are quite also the majority choices that were found empirically. So again, the neo-additive gives good empirical results, another success for the theory. Now comes the next modification that we will in fact skip, but let me say a few words. All the analysis I did so far and everything you learned in previous game theory courses, almost everybody of you, was assuming that players play deterministically in the sense they always choose what is best. And well, we do allow randomization, but then they only randomize between all the things that are best anyhow. I mean, you know for sure that they're randomizing. But in reality, it's more realistic to always reckon with mistakes and confusions and all kind of weird emotions to always assign probabilities and maybe non-zero to all kind of strategies to analyze game theory in a probabilistic manner. Well, that would be coming in chapter 8.2 with a beautiful concept of quantum equilibrium response. But we have no time to do it, so I'm going to skip all of that. I'm going to skip all the slides, and I'm going to continue after this with section 8.3. That will be the next recording.